We close the door, maybe leave it open.
Okay, I'm good.
Okay. Good afternoon, everybody. I'm Moody Sagif from Satora and Tel Aviv University. Excited to be here. Maybe just raise your hand. Who are you? Solidity developer? Maybe sorry, Rust Solana developer? Solana, Solidity, and form application, everything. And you, the other?
Cosmos, and I do Rust contracting.
Amazing. And the other person, you also Rust? Okay, great. So feel free to stop me or Harman. We are, it's a kind of a last moment thing for us, but we are going to be next week in New York, and we're going to do something much more extensive. If you are there, please, I know one of you, so please come. So this is our attempt to do formal verification, and I give you an introduction which is made for smart contract developers.
In the space.
Okay, so this is taken from Wikipedia, formal verification. How many of you have heard of authentication, maybe? Also have authentication, formal verification. Okay, yes, amazing. So this mature field of computer science, maybe one thing to say that it's obvious, especially for people who try to apply formal verification for hardware, is that formal verification is not just about proof, it's also about bugs and finding, and especially people have done it in hardware, but we see it also in software. It is part of the reason of formal verification is to find bug early, before or after auditing or any other process. As you can see, probably I've been around for quite some time. So this is somehow how I look into this field, and it's actually interesting. Many fields of computer science or actually of science go to a period of time. So formal verification dates back to Turing, the inventor of computer program that already in looking to his 50s paper, he's talking about concept like formal verification in a very, very clear way. And then there is a period, I call it the golden period. Maybe I'm not quoting all of them, but these are people I actually now collaborate closely. I'm actually at NYU with Patrick Cousseau. The rest of these people are all giants who invented this field. They have, all of them with the exception of Cousseau, have Turing Award, which is the most important, distinguished prize in computer science for contributing to this idea. I'm sure you have heard about them. So they actually sort of told you about formal verification, and they promoted formal verification. And this was the golden period. A lot of people talked about it. It looked like a good thing. And then what happened is interesting. In the 79, there is a paper by Richard DeMillo. How many of you know of this paper? None. So you should take a look. It's very interesting. It's one of the most destructive papers for formal verification. So this paper explains why formal verification will never work. Okay. And it's interesting, actually, this paper, it's interesting that it's a bit before I started my career, but it's interesting. This paper caused a lot of grief to many, many people in this field, sort of explaining why it's not actually the right thing in some sense. And it's a very interesting paper. You could argue if it's useful or not. I kind of started my career somewhere here. And I usually know it, and this is what I did all my career business. I want to go against stream. So when I started, everybody was zero knowledge, cryptography, and all my friends. So I want to do something else. And I decided I take something which is not attractive, so I can. So that's why I picked formal verification. And I've done many works with, and a lot of people have done good things. I'm mentioning the Yikes tool, which SI, CVC, Z3. These are amazing formal verification tools built by the community. Here you see a very nice quote by Bill Gates on formal verification, which I'm particularly happy because it's essentially about algorithm that I wrote, which was implemented by the Microsoft research team. So it's a nice thing. You see that he's saying here that it's in fact getting to work in a device driver. It's a different field, not Web3. It's a Web2, of course. But the idea is that this field is coming, and I think Web3 is an interesting domain. We are seeing a lot of things going in formal verification because it's increased the level of trust. We'll talk about it. Okay? So I think it's like, by the way, AI also went through the same thing. There's down and there's up. I think it's interesting. There's high, down, up. Many feeds go this way. So I think this is, I hope we are, I don't know.
Up only.
Sorry?
Going up only.
That's, I do not know. You, okay. So that's the idea, right? So what do I do here? Okay, so actually I want to think, so in the last 7 years, we've been working with very, very, very good protocols in this space and the DeFi space, particularly lending. So this is actually coming from our client using our tool and basically checking, basically we prove properties, and then they started inserting bugs, and they see that actually the tool catches them. So it's interesting. So this is I'm sure many of you know, it's taken from communication science. Okay, so the idea is that you go to your boss and you get feedback or something like this. Okay, so this is what's known to you and what's known to the hacker or whoever. You can think about this way. And the idea is if you go to auditors like us and many other, we can tell you about blind spot and others. But what formal verification can do, if you write the right property, it can somehow prevent you from things that are not necessarily known. Because if you know the right property, this is how it's increased the trust in your code. Okay? Why does it say? Okay, so this is actually a very nice quote by Vitalik. Do you know why he wrote this quote? Actually, it's a very interesting when and why he wrote this quote. Do you know, Gregor?
About the KVM security?
No.
Oh, when or when?
This is, no, we see it. It's actually
August.
August. But why?
After a hack happened, closed source protocol?
It's an unfair because I have knowledge on it. So this happens after Pavel was arrested from Telegram. So the idea is that if you have a formal verification, then we can perhaps convince authorities that we are doing things in the idea. So this increases the trust in the code. That's the idea. It's increase the trust in your code. And this is actually, I told you, after our own tool, actually, that we bring formal verification, make it almost standard, and trying to work with DeFi protocol in Solana, in addition to, and with the Solana Foundation themselves on verifying the SPL token. So we are trying to make this technology useful, and we'll see with the workshop, we are making baby steps, and we have this tool, we open source it, it's a huge code base. So here is a comparison. I know here, verification. I'm not actually comparing only formal verification here, and I'm also, this is not exclusive. There are a lot of other tools, including in Web3. So these are tools, and then you can argue even our tool. I mean, the Slither is a static analysis tool. People are building now static analysis also for Solana. It's very useful. It's very easy to use in a sense. It's, but it doesn't give you good security. Foundry and other fuzzers, including the one by Asymmetric Research, they are good. This for EVM, but you can do it, of course, for Solana. They give you security. It's very easy to use, but it's harder than Slither because you have to write these properties to get the useful result. One verification, they are actually pioneers of using the K system, including for the verifying the EVM itself. The nice thing about this technology, it's agnostic. It doesn't actually, you can apply it to everything. But then you have to humanize, you have to come up with a proof for everything. We are not going that way. We are trying to do something that is specific to that and try to make this tool so that the effort of writing a proof of a single program is easier. That's what we are trying to do. And Amazon, actually, it used to be Microsoft. They have a beautiful tool called Lean. How many of you know about Lean? Okay, so one. You should learn about it. It's a big competitor for Satora, but it's interesting. It's a very interesting tool. It's still very hard to use, but it's actually a lot of things are very, very moderate and interesting, including the inclusion of SMT solver, many other things that to make formal verification easier. And our tool, which we have worked a lot and spent considerable engineering effort in terms of people, and I acknowledge Jorge and Ari and many others in our team. We are supporting EVM, we are supporting Solana bytecode format, WebAssembly format. We are giving security, and we're making it hopefully another step from fuzzing, but still way easier than what people call proof of system. The thing we are particularly happy about, which you don't have with proof of system, is the ability to find bugs. And a lot of people have used it now, including Immunify and others, to find bugs. That's a very interesting thing. And also that we integrate into your CI. You change your code, and unlike proof of system, you don't need to rewrite the proof. You just need to rerun the tool. Okay, so this is the benefit of formal verification. These are the benefits of formal verification. Of course, we're not inventing anything. I think the most interesting one for me is the first one, and we see it from our case, and I'll show you it from our client. It's a case that you run this extra mile and you find bugs that really hard to find in auditing, in fuzzing, in others. So you find these rare bugs. And another thing is that you maintain changes of the code. We know like cases that you have oil there and you have normal. People did change one line, then 200 million were lost. So you want to keep your code base safe. I think this is actually interesting. They're writing the spec, and actually, this is actually, you see here from a recent client called Manifest. So Manifest is building a very sophisticated order book. I'll talk about it later, but basically what happened, we worked with them, we wrote the spec, and by writing the formal spec, it's increased their understanding of the code. And in particular, we were able to, in one case, we were able to really drastically simplify the code with this. And now Aave is coming up with V4, and in fact, part of the things that we do, V4 was designed for formal verification, and we make it simpler to make it easier for formal verification, and it's also probably easier for auditing and other things. We're making it easier for formal verification and more understandable, actually more gas efficient. Okay, it's offers proof. This is what the Darkstar thing, and also the other thing, formal verification is by definition hard, but the fact that it's hard make it sort of people that they see that you do something more. And we already see that it's a binding issue. It's a binding for Microsoft, but it's a binding also for Aave. It's a binding for many protocols. For example, we had this Euler protocol, which was hacked. Then they formally verified the code with us, and then they ran a $2 million bug bounty, and nobody found the bug. And now they're trying to gradually earn the liquidity. So formal verification gives you this extra binding. That's the idea. Okay. Why does it matter for Solana? So you see that Anatoly is very happy about it, which is great. Squad, which is our first client, they use it to secure the wallet. And you see also that Anatoly is very positive about formal verification as a way to increase the security in Solana. So what we are hoping is that Solana is already making progress. By using formal verification, we can actually help it even become more secure and more robust and trusted by other people. So to approval, just to summarize, we are the company who provides manual audit, but we are also providing formal verification. You see, originally it was for Ethereum. Now we adapted it for Solana, and recently also we adapted for Stellar. So we adapted it for, now we are in the process of adapting it for another blockchain. So we are adapting it to more blockchain to make this technology available for Cosmos actually. So we are discussing with the team. So, and another thing that the community pressed us for many times. So we, after 7 years, we decided, and this was even hard internally to convince the engineering, but it's all open source now. It's about 500,000 lines of code. It's a huge code base. It's all open source. Go and break it and use it and whatever. And it's not formally verified. It's pretty tricky. And in fact, it's not just formal verification. I'll show you. There's static analysis, there's decompiler, a lot of things are there. A lot of things there. There's clever data structure, a lot of things that we had to do to make this work. So we make it work for Solana. You see, we apply it for Jito, Camino, Squad, Solana token extension, Manifest, now Texture. And we are working with more now. We're working with more, actually coming 2 or 3 more protocols soon. We are working with protocols that we, at the moment, write formal verification rule for them. And the reason for this workshop, we want people to write rules on their own. And it's a free version. We want to encourage this. We have in the Ethereum already. We have teams like Maker, Morpho has been using the tool, but we want to have more users here, and that's the reason for this workshop. You see some quotes. So you see that actually a nice quote by Camino with the leading lending protocol, and you see Jito working with us and working with another security company, Autoset, and Asymmetric Research also a very nice company. I mentioned that they do further. So basically, we are playing an important role here, and we give in addition to auditing, we give the formal verification angle. You see here also that we have other quotes. You see that also the quote of the squad explaining how we secure things in V4. It's interesting thing that we on our own find out that sometimes we put the best security researcher and the tool actually is able to find issues after us. So it's actually complement our services. How does it work? So that's a bird's eye view, and Armin will show you. Also, you write the spec. The spec is written in a kind of weird version of Rust. So essentially, you write your program twice somehow. You write the code in Rust, and you write the spec in Rust. But the spec is much more declarative than the code. And the spec also contains some properties which are not programmable, because it's not meant to be run. Okay, so it has some things. You will see, Armin will show you. And you essentially compare this. You can think about it like a smart diff. It's trying to find behaviors here which are not here, or vice versa. And if they are the same, then in some sense we are saying it's proof. The most interesting thing is that it tells you that they are different. And unfortunately, since we decided to work in automatic tool and to rely on SMT solver, in some cases we will not be able to prove a property and will not be able to disprove a property. So this is called timeout. It means that we waited too long and we didn't get result. And we have a lot of techniques to eliminate timeout, but at the end, if your code is complex, this may happen. And then you have to do things which you do in other prover. You have to modularize the code. You have to simplify the code. You have to do other things to make the prover more happy. Ask me any question if you have. Okay. So this is how it feels like. It feels like this idea. You see this, and you have this language CVLR that we wrote spec, and you can write your own spec. It's an open source language that we wrote spec. By the way, these specs are also useful for fuzzing and other things. They're essentially spec that you can use. It's a similar spec that you use in fuzzing. It's a spec that says what you behave and what you expect. Inside, it's fairly complex. We have go to the LLVM, which is internal representation, and then we go to the Solana bytecode format. We don't trust the compiler, which is the decision we made. Maybe it's a mistake, but we have found bugs in the compiler this way. So we decided to verify what is actually executed. And then we have a lot of things. This is actually the clever thing. We are trying to make static analysis that simplify the code. So we are actually don't want to analyze a lot of complication in the code related to storage, related to aliasing, that we have algorithms that are able to recover things. And then we go what's called verification condition generation. We essentially convert the code into a mathematical formula that actually describes all the behavior. So we are not actually executing the program. We are essentially converting the program in a mass. And then we are calling off-the-shelf solver. They are solver developed in academia and in research institute, and we are trying to get them. In some cases, they are giving us proof. In some cases, they are giving us bug. And then we try to make it more accessible to the user. So this is many sophisticated things, and we have work on it considerable amount of time, and we love to get contribution from the community and from, so it's actually now academic people are trying to and starting to contribute here, which is good. Maybe just want to give you a few examples. Armin will give you more. So see, this is a very simple function called check fee. So you see that we add this bold, these are the spec here, okay? So CVLR assume it's like a require. It's making some assumption about the input. So you assume that something about the amount that is greater than 0. You assume that the BPS is less than 10,000, and then you have a set. You have the so this is the precondition. This is our assumption at the beginning, and this is the post condition. And it's similar to what you do with fuzzing, but notice that it's a bit different because in fuzzing you usually start from a particular state. Here you are starting from an arbitrary state. So this is what we usually call proof by induction. So this is for good and for bad. If we verify that, we verify that it's okay for arbitrary state. And for arbitrary state, we satisfy these requirements. And this is what we try, and essentially you notice it's a fairly complex code, and I can show you the bytecode is fairly complex. And you see that, what do you want to guess if it's right or wrong? This code? You're probably a better developer than I. I wouldn't be able to guess. So it is wrong. Let's see. We run it. And there is a bug here. The bug is actually it's a tricky bug. It's a tricky bug. It's actually used very often, even I think 2 weeks ago, by many people to steal money. It's a rounding error issue. There is a case that this div is implemented with a floor, and it's under the hood, and then in a certain rare situation, a hacker can actually get this value here 0. So let's see. I asked Jorge because, so you see the BPS 1, AMT is 5,000. It's very, very close to 0, and then because this does a floor computation, essentially under the hood, so this is a very rare situation. You don't. It's of course, if you give this input to a fuzzer, it will find it. But how will we find it automatically? Okay. So that's the idea of this kind of bug. Interestingly, you see you can fix it because you use another API which actually calculate correctly. And now we are able to give you a mathematical proof that every time you start with a state like this, it verifies a property like this. So that's the way you would usually work with the proof. When you write a rule, it is violated, you check it out, you say maybe sometimes it's a bug in the rule, sometimes it's a bug in the code. In this case, it was a bug in the code. It could be also a bug in the rule. Okay? So this is it. What is going on here? So maybe I give you another example, which is more complex code, is Camino. This is, I think, the most sophisticated lending protocol on Solana, and it's manipulated significant amount of money. And the interesting thing is that we came to the game after they completed testing, fuzzing, auditing. So we came and we tried to apply this technology. And the interesting thing, we can both find bugs, and more interestingly, we can prove properties. And these are actually, we do it together. So you see, we prove several properties. We prove here that the amount of shares remains okay, and also actually after every operation, the division of the shares you're not diluting the shares. And the last thing I think we showed that it's similar to what we showed for Euler, that you have sort of the LTV, the loan to value, is always less than the threshold, which means that you always have enough collateral to cover your loan. So this essentially means solvent. So we prove these properties formally on the code, and it's interesting because this is a code which is complex, it's executable, we're not trusting the compiler, and still we're able to prove these properties. This is even more complex. This is the manifest. Are you familiar with the manifest? Some of you are. So it's an interesting protocol done by the designer of the open book. It's a new version of the open book. It's supposed to be way cheaper. In fact, it is way cheaper. And the idea is you jam all the account in one account, actually. And this is done due to a clever data structure, which is a bit tree, which is a binary tree, but it's jammed inside. And we prove properties of it. And interestingly, this is a case which you have when you have tree data structure, you have tricky mistakes that you can have. In fact, after fuzzing, we found many tricky mistakes by checking that in fact it's the same of the reference implementation. We check the data structure correctness, including balancing. We check all the operation with formal methods. So this is it. And we actually it requires you see this is red black tree, so it requires rebalancing and sophisticated operation. And we verified that. You can see all the property, and we also detected the bugs which were fixed by the team. As we said, one reason is to want to make this tool integrated into CI. So you see that every time you integrate into CI, you run it, and actually this is now working on the manifest team. They integrate it, so every time you do a change, you run the prover again. So actually this is in the squads, another team, you integrate it into CI. That's we said we have this first and formal verification for Solana, and it's open source. I'm close to the end. I just want to tell you a few things, maybe they're obvious, but still, formal verification, and that's actually something that's been around for a long time. It's not actually producing a bulletproof code. There are a lot of things which is hard to prove with formal verification. Also, it's not, people say that they use it instead of auditing. We see it's actually complementary to auditing, and actually we are seeing auditors using our tool, which is great. And it's not actually something you want to do late. The earlier you do it, the better. Even at the design level, we have incorporated. And also, we want to make it so that everybody can use. And this is the step. We want to make it so that every developer can use. And we want to make it almost as easy as unit test. How do you work with us? So the obvious thing, take this software and use it. And we have already a team using it. That's great. You integrate it into your CI. We have a GNU license. It's simple. If you have a bug, we report it and we try to respond within a week. But of course, we sometimes busy with other clients, but at least we respond and tell you what is the issue. It could be a bug in our case, it could be a bug that you don't understand something. We have a fairly extensive documentation, but we keep doing more. And in Solana, it needs to be improved. It's where Armin will show. That's the first one. The second one, people who can afford, it's not very expensive. We have clients using the tool integrate into their own. Basically, before or after auditing, you pay because you get access to powerful machine, and also we help you in consulting. We help you in consulting if you have issue with the rules. We help you with consulting, and if you do auditing with us, we also make it cheaper for you, but you don't have to. You can use it in addition to auditing. And the last offering, actually, that's, I think, the most appealing for protocol with significant funding, and we are doing it. We know that formal verification is not a bulletproof, but we, Satora, we have 7 years of experience, and we did miss a few critical bugs, but we believe that the rate of us missing the bug is very low. So that's why we are putting our money where our mouth is. So if you engage with us, I think, and we are the only company in this field, we are willing to, and if somebody finds critical after us, either a white hacker, a black hacker, we are willing to pay 200% of the money that we got. So we are actually giving, so this is, of course, if we write the rules. In the future, maybe it will be for people that they write them, okay? But that's the idea. We want to make it so if you, and we have already few customers that are doing that. So we believe, and of course it doesn't mean that if you formally verify this, it will not be hacked. I mean, if it be hacked, we will pay. Okay, that's because we know that there are some limits to formal verification, but we also have fairly confident in the code that we formally verify. And people have tried, like in compilers, people have tried to hack compilers which have been formally verified, and they have found ways to hack them, but they found that they are more robust. Okay, and so when we cover about any critical issue, whether we wrote the spec or not. So I think I'm done. Now, you have a question for me, or otherwise you go to the more interesting stuff by Ahmed? Yes.
Can I ask you a question? Have you had a case before where you actually had to match the bug bounty, or is it like never happened before? Just wondering.
So the answer is that we never had a case, but there were cases that we decided to. So there were cases that we decided to for various reasons because we felt like we could have done better, but it not that we were obliged formally. But now we will have to oblige. But it's definitely the case. I can told you we had a client who was using the tool and they were doing an amazing job, but they wrote something which is called tautology. You know what's tautology? Tautology is a property that says it holds on all inputs. Basically, for example, you prove that 7 is greater than 5. Okay, and so the tool is able to prove that, but it's not interesting. And then somebody found a bug after them. And the problem is that the bug was not, there's no bug in our tool. The spec was missing a property. Okay, so we, at this point, we want to help you. And we have, if you run the Sator Prover, you see a lot of things. There is some case that you check tautology, we check some things to make sure that the spec is okay. We do some best effort because we understand that you can have bugs in the spec. We understand that writing spec is hard, and you will see later. Yeah, thanks.
Thanks.
Other question for the team? Okay, Armin, you?
Sure. All right, so you guys give you a chance to try some stuff out. If you want to scan this, it's a QR code to a tutorial repo. The tutorial repo is going to be finalized next week, but right now most of the early stuff is there. It's a Vault implementation, similar to like the Vault standard in Ethereum, but it's implemented in Rust. It's not too complex, but it's not super simple. I'll probably show you like one property, and I'll challenge you to finish another similar property if you'd like. So how can I leave this up here? Well, yeah. So I have a different desktop I'd like to open.
You want to call the guy?
No, I think I know. I go here. Okay. So just real quick, this is what CVL looks like. We only showed you a little bit. These are some rules. These are the docs. You can access them at docs.sator.com and go to the Sator Solana Prover. Yeah, and basically it's restating some of the things we already know. We have pre and post conditions. Similar to a unit test, but you get a proof and it's symbolic. So you get an arbitrary state. This might be too small, huh? But you can see it. Can you see it? Okay, so here you can see this is the actual function in Rust. It's put it in the spec file just for convenience here. It's a simple function, right? You take the fee, you have the fee amount, and then you calculate it. You multiply it, you divide by 10,000 to get the amount. That's the fee. So, and then you have some properties here, right? So you have the satisfy statement, which we haven't shown, and it's a little more confusing, but the assume and the assert are pretty straightforward. The assume, you just say, assume this is true. So take an arbitrary value, filter it so that this is the only type of arbitrary value we have. So this is basically any value that's less than 10,000, and then move on. And the assert says, if this is not the case, then give me an example where it's not the case. When the example includes the state of the contract before, the program before the function is called, the function inputs, and exactly how it's done. And so the satisfy, it just says find one example. Maybe I could, you could see the satisfy is that it's violated when it is either not reached or when every execution it reaches violates the condition. So it just says find one case in all of this arbitrary state that can reach this condition. So those are like the basic building blocks of rules. And then so I'll show you an example. This is the repo. I just made it public recently. You can try to go to it. It's just my username. It was the QR code before. And in here, this is the Vault implementation. And here you can figure out, you can get like a key to be able to run the tool. And this explains the Vault and everything. But the Vault just has some deposits and withdraws. And I'll show you one rule where, we prove something about those deposits and withdrawals. So you can see there's a ton of work here that you can read the README and walk through it on your own time if you like, but I like to show you, so this rule. So you could see we define some variables. Also, I didn't talk about this non-det. Maybe I'll tell you really quick about the non-det. Non-deterministic value, it's just like an arbitrary value, but it's, it just means, you could, maybe this sentence is best. Similar to arbitrary value, but it's not random. So it's explored exhaustively. It's symbolic. So you get all these inputs for your function, which are going to be symbolic, and so is the state. So all the balances of any account, all the token balances, any positions people might have. So if it's like a trading or lending platform, all that is arbitrary. You call some function here, and you can have, and you pass those inputs in, and you make an assert. So here we're just saying that, if you deposit some funds, then the total assets should increase, right? And for you, if you'd like to try to run this, first go to the link in the README of this repo.
I'm confused, but they had to get the user.
Yeah. So if you go to the link in the README, it's here. You can go installation, visit tutorial, and there's like a link in the README. It'll open you to this page, and you'll get a key.
In principle, of course, you can run it also locally on your own machine, but it's complex. It's much easier to run it on our machine.
Yeah. And then once you have the key, the easiest way is you don't even have to install the tool. You can just go, here, and in code spaces, you could just create a code space. And this will set things up. So now we're in here. I think my terminal hasn't loaded. While that's happening, I need to copy my Sartorial key. While that's happening, I'll have this. Yeah, my computer is slow. So I'll leave this here while that's loading, but you go to the repo, you get a key from the Sartorial website. You could also just go to sartorial.com, and it'll be like right here, get started for free. And you just like put in your name, and then you get a key in your email. In the meantime, have you guys used any tooling like this? I assume you have, but like you use testing or fuzzing or no?
Foundry and Certora with
Foundry.
the EVM.
You use
Nice.
Foundry or the EVM?
Yeah,
Oh,
Foundry and Certora on the EVM, but I haven't done Solana.
Yeah.
Can
What
you
about
tell-
the Cosmos? Are you using any tool for fuzzing? Or
No.
there are no fuzzing. So it's only the generic Rust fuzzer, right?
I'm just not familiar with it.
For most systems, did the formal verification tool, I think.
They use TLA plus.
They have TLA plus,
Yeah.
right? But yeah, did you try it?
No.
So this is probably like a OPSEC issue, but you can get your own key. You don't need to copy mine. So do that, export your key, and then you can go into programs, vault, source, Certora, specs, comps. No, Certora, comps. And then you do Certora, Solana, prover, and you run the integrity. Solana, prover, Solana. What? Certora, so. So maybe the code base is, it told me the code space is broken and I ignored it. So I have to restart this thing. Okay, so just to maybe save some time to show you something interesting, you do that command, you run one of the configuration files, and you get like a link, and that link will bring you to something like this. So you can see here there are the rules, and here you can also see all your files. You can see I have all my source files, I have all my Certora files, my specification, and for this specific one, we ran the integrity specification. Which rule? I think we ran this rule. So the challenge is to finish this rule, so you can cheat, but it's you can copy. They're similar. So and you can see like the rules in here that were ran, they all passed except for this one, rule / no dilution. You can see that here, like you get the check marks, you're happy, but actually this rule was violated. And you could see the call trace here. You could see what the values were. There's a way to pretty decimal. So you could see like the values and what was done. I could show you the slashing function. So I can explain. So this property that we're checking, and you could like jump the file here to show you exactly the property. It just says when I call the slash function, then my ratio of assets to shares remains the same, I believe. Oh, this is the contract. So you could see, yeah, the slash, we call the vault process slash, basically the rule is not super interesting because it just says something that's not true, but the idea is to show you a counterexample. We call the slash function, which just removes assets, and then we assert that the ratio of assets to shares stays the same, which is obviously not going to be the case since you just slashed some assets. And then you get a counterexample where it tells you, okay, you started with this state, you started with these values, and then this function was called with these inputs, and then you got a result that violated the property you wanted to verify. And then, in a normal use case, you'd think, okay, what's going on? What is this a bug? Did I write the rule wrong? Obviously here, the rule is wrong, right? Because the property simply doesn't hold. And maybe if the slash was slashing both the assets and the shares in equal amounts, or, then you can have this property. Yeah, since we have this technical issue, I don't know if did anyone else try to run the code space? Okay, so if you're interested, you can go to this repo and follow the instructions in the installation guide here to install the tool directly and not use GitHub, and everything should work fine. And you can get a key and try to run some of these things. And the idea is to, if you're developing smart contracts programs, you can use this tool to prove properties about your code and, build confidence about your security, go live, beta test your stuff. Yeah, thank you guys. Happy to answer any questions. Stop sharing.
Do you actually have some, can I ask you a question? Do you actually have some of the clients who does write, like they maybe train someone internally and write CBL spec themselves and they just use the tool themselves?
Yeah. Like most of them, actually all of them are on Ethereum for now. It's a lot more developed, the tooling. We have a whole language for it. But yeah, like Morpho, we have different slides with all the names. Maker, yeah.
So just kind of support them a bit, like they're taking care of full verification internally, sort of.
Yeah. They have like usually a dedicated person that is like a formal verification, that they're like security person, or they have a person for formal verification. And we have calls with them like usually weekly or whenever, and we support them, and they, we help them insert bugs in their code to check that all the specifications actually are, what the coverage is, what bugs you would find. Tell them, hey, this is actually a tautology. You want to write it this way. Yeah. Okay. So I'm going to stop this stream.
Up there.
Sorry.
Yep.